Hello students, I hope that all of you will be fine and staying at home in this lockdown period. Last week we have done Euclid's division lemma and fundamental theorem of arithmetic. Today we will be discussing some more questions related to the chapter real numbers. So I am explaining second question of exercise 1.1 of NCERT book, page number 7. Question is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Now, solution is, we have to take, suppose that let A be any positive odd integer. Apply the division algorithm with A and B equals to 6. Why we have taken B equals to 6? Because in the question we have to prove that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. That's why we have taken b equals to 6. Now, according to Euclid's division algorithm, we can write a equals to bq plus r, where r is greater than or equals to 0 but less than b. Now, since we have taken b equals to 6, so we can write a equals to, in place of b, we can write 6q plus r, where r is greater than or equals to 0 but less than 6. Now, in this case, the possible values of r can be, because it is greater than or equals to 0, so 0, 1, 2, 3, 4 and 5, because it is less than 6. So we can take the value of r 0, 1, 2, 3, 4 and 5. Now suppose if r equals to 0, first value. So if r equals to 0, then a equals to 6q, because a equals to 6q plus r. If we take r equals to 0, then a equals to 6q, and we can write this as 2 into 3q. 2 3 is 6, so 2 into 3q. Now 2 is a prime factor of 6, so which means this number is even, because 2 is a factor. Now, if we take r equals to 1, then a equals to 6q plus 1. In place of r, we can take 1. Now, if 6q is even, after even number there must be odd number. So it is odd. 6 cube plus 1 is odd. Now r equals to 2. Then a equals to 6 cube plus 2. So it means it is again even. Similarly, if we take r equals to 3, then a equals to 6 cube plus 3. It is odd. If r equals to 4, then a equals to 6 cube plus 4, which is again even. If r equals to 5, then a equals to 6 cube plus 5, which is odd. So we have taken all the possible values of r. Now by this table we can see positive integers are of the form 6q plus 1, 6q plus 3 or 6q plus 5. This we have to prove. So therefore any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Now next question is question number 4 of exercise 1.1, which is use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. This is again the same type of question which we have done earlier, that is question number 2, but method is slightly different because here we have to prove that square of any positive integer. Let us start. So again, let a be any positive integer. Apply the division algorithm with a and b. A and b. Now we have to take b because in this question we have to prove that either of the form 3m or 3m plus 1. So we can take b equals to 3. Now if we apply Euclid's division algorithm, we can write a equals to b cube plus r, where r is greater than or equals to 0, less than b. So a equals to, in place of b, 3q plus r, where r is greater than or equals to 0 but less than 3. Now what are the possible values of r? We can take r as 0, 1 and 2 because it is less than 3. So first case, if r equals to 0, then we can write a equals to 3q because r is 0. Now we have to prove that square of any positive integer. So squaring both the sides, we will get a square equals to 9q square, which can be written as 9 can be written as 3 into 3 into q square. Now in place of 3q square we can write m, because it is given in the question that m is some integer. So if you take any value of q, it will be an integer. So 3m. You have to write here, mention here that m equals to 3q square. So it is square of any positive integer is of the form 3m. This is first case. Now second case, if we take r equals to 1, so we can write a equals to 3q plus 1. Now again squaring both the sides, left hand side will be a square, but right hand side we have to apply algebraic identity, that is a plus b whole square. This means a plus b whole square is a square plus b square plus 2ab. So we will get 9q square plus 1 plus 6q, 2ab. Now we have to rearrange it. 9q square plus 6q plus 1. Now in the first two terms you can see 3 can be taken as common. So in the bracket 3q square plus 2q and plus 1 will be written as it is. Now again this bracket we can assume that it is m. So 3m plus 1, where m is 3q square plus 2q. You can take any value of q, it will again be an integer. So this is the second case. Now the third case, if r equals to 2. So we can take r equals to 2. So a equals to 3q plus 2. Again squaring both the sides. A square equals to 9q square plus 4 plus 12q. After rearranging, 9q square plus 12q plus 4. Now 9q square plus 12q, in place of 4 we can write 3 plus 1. Now in the first three terms again 3 can be taken as common. So 3 common, in bracket 3q square 4q plus 1, and this plus 1 will be written as it is. Now this bracket we can take as m plus 1. So 3m plus 1, where m is 3q square plus 4q plus 1. So you can see square of any positive integer is of the form 3m, 3m plus 1, 3m plus 1. In all the cases, we have proved that square of any positive integer is of the form 3m, 3m plus 1.